So we're going to take the Rutherford experiment one step further, scattering alpha particles from gold foil or from anything. Last time we calculated that the scattering parameter b as a function of theta. In other words, if we are within a distance b of a scatterer, a nucleus in the gold foil, then we should expect the thing that scatters to be at the to show up at an angle theta away from its original path. Now we're going to ask how many particles should scatter at an angle theta. We can figure that out from the impact parameter b. We're going to start by calculating what's called the scattering cross section. The scattering cross section is simply the area with radius b, meaning if let's just think about a scatterer, the nucleus in the gold foil, looking head on, the alpha particles going into the page, and that any alpha particle that falls in that area, right, within, keep on forgetting what B is called, within B of the scatterer, it will scatter at an angle theta or greater. Right? So that's the scattering cross-section is the area within which a particle that is scattered will scatter at angle theta or greater. So in order to go ahead and figure out how many particles actually scatter at an angle theta, we need to know how dense the scatterers are. So we define the n, which is simply the number of atoms per unit volume in the scatterer. So that just has to do with density. And also T, which is the thickness of the material. So that therefore, within a certain area and thickness, which is a volume, we would know the number of atoms. So we define those two variables. Again, if we imagine that we are looking head on at this gold foil, then the number of atoms per unit area that we will hit, that we will see in any area, is n times t. So therefore, the fraction of scattered particles that will scatter at an angle greater than theta, the fraction of particles that are within a distance b of any one atom, is going to be nt times sigma. So plugging in the cross-section and the impact parameter, you get this. And by the way, this derivation is done directly in the book. So if you want to see it a second time or done maybe with slightly more detail, you can also look in the book to follow along. So I shouldn't go into too much more detail because there's no point in me doing exactly what the book says. So you can just take the derivative of f with respect to theta, and therefore, right, solve for df in terms of theta. You can just go ahead and do that. No need for me to redo that here. That the number of particles that are scattered at a certain angle is going to equal the total number of incident particles times df. Actually, wait, that's not quite right. I have to be careful here because what happens is as these particles come in, let's look at it from a side view again. As these scatterers come in and they scatter off the gold foil, they're actually going to scatter in 3 dimensions. It's kind of hard to show that in 3 dimensions, but they're going to scatter into a ring. They're going to scatter into a ring. This is actually, again, this derivation, I'm not sure how much of it I need to do because it's in the book. And the book draws a better picture, but it'll scatter into a ring. That's supposed to be in 3 dimensions, not a very good picture. And the area, and there's going to be, because there's some width to that, right, this is a real experiment, some width to that ring, which is an angular width d theta, then the number of particles that scatter into that ring is going to be equal to n, the total number of particles, times times df, the fraction of particles that scatter at a particular angle, divided by dA, the area of that ring. And so therefore, n of theta. Now go ahead and plug in everything, take derivatives, etc. What I'm really interested in is getting to the end result and not worrying too much, as long as you understand the basic principles behind what we're doing here, and seeing that the end result is It's not like I'm going to ask you to reproduce this particular derivation on an exam or even a homework, just to use the results and understand the results. So what we're getting is there's a lot of things here, right? Ni is the number of incident particles on the foil. N is the density of atoms in the foil. And T is the thickness of the foil, right? So this is our foil that we have these alpha particles scattering off of. And Z1 and Z2, I can't remember which is which, doesn't matter. One is the number of protons, or the charge of the alpha particles. Z2, the other Z is the charge of the gold foil. R is the radius of the ring in which we're looking for the scattering events. K is the initial kinetic energy of the alpha particles, and theta is the angle at which the ring is. Bottom line is, what's kind of amazing is that this really works. That if you go ahead and apply this equation to the scatterers, you will get you'll be able to see the number that this predicts at given angles that are scattering. So just looking at this equation a little bit, can talk about the fraction of the total number of incident particles and theta over Ni, and that is, you can see that's proportional to the charge of each of the scatterer and scatteree. It's inversely proportional to the kinetic energy of the scatteree. In particular, I want to see how it depends on angle, right? It's inversely proportional to the fourth power of the angle over 2. And let's just think about, so I think that the sine to the fourth of theta over 2 looks something like that. You can see that it is a minimum at 0 degrees, and it's a maximum at 180 degrees. So that tells you that it's much more likely for something to be forward scattered than backward scattered, or more likely, right? Because 90 degrees is forward scattering versus backward scattering. This is forward scattering, and this is backward scattering. Okay. Oh, and just in case that wasn't obvious, and the fraction that are scattered through an angle is the inverse. That's why this indicates it's more likely to be forward than the larger number, which is backward. Just do a quick example. They're all kind of plugins. You just got to find the right relationship, and it's really a question of understanding the relationship. That's why they're important. But once you find the right relationship, it's plugging in. So let's ask a question. What is the ratio of alpha particles with energy 4 MeV that scatter to angles greater than 90 degrees compared to 45 degrees, let's say. If we're just doing a ratio, it's going to be F90 over F45, and nothing changes except for the angle. So we've got the cotangent of 45 over the cotangent squared of 45 over 2, 22.5, which is equal to, so it says that 17% of the scattered particles scatter greater than 45 degrees, actually scatter greater than 90 degrees, right? That's what that says. 17% of those that scatter greater than 45 degrees are at an angle greater than 90 degrees.